without human input. But even the first-person example that I'm trying to give, that you could have a first-person view of whatever the drone sees and you could teleoperate sort of. But even that would, in the context automation, you would not even need that. So you could train the drone just based on computer vision where to spray, let's say, some pesticides. Yeah, so human operator would become arbitrary in any way. Right. So thank you so much. Let's take this.
Thank you, Dr. Shehzad Rasool, for showing us the potential of AR and VR technologies in enhancing agriculture practices. Next, we will hear from Jakub Pawlak, a PhD researcher at RPTU, Germany, who is joining us online. He will be discussing unsupervised learning in robotics, focusing on how machine learning is enabling autonomous systems to make intelligent decisions, particularly in agriculture. Mr. Pawlak studied computer science at TU Kaiserslautern from 2014 to 2022 with a focus on robotics and artificial intelligence. His master's thesis entitled Domain Adaptation for Synthetic Images to Real-World Scenario Using Generative Methods dealt with the effective use of synthetic data in the context of machine learning. Since 2022, he is pursuing his PhD at Robotics Research Lab, RPTU Kaiserslautern, and continues his research interest using generative deep learning methods like GANs and style transfer for robust perception in robotic system. Please join me in welcoming Mr. Jakub Pawlak virtually.
Unsupervised learning with embodiment. Yeah, maybe you can turn a little bit the voice down because I can hear myself. Okay, yeah, now it seems better. It's great. Thank you very much. So, a little bit about the motivation behind this work. So currently in our lab and in many other labs and companies, the kind of general pipeline of running machine learning models is kind of like this. So we take we pre-train a model on a static data set, we deploy it on a robot, and then just run inference, and maybe we do some object detection, segmentation, or whatever tasks we have in mind. But this is actually the same process as it would be on a standard PC or just on a server in the cloud. So there's basically not that much difference in the way we kind of run our models. However, my thesis or my hypothesis is that basically a robot is not just a static system. It has a physical presence in the world that it exists in, and it has way more possibilities than just a static piece of machinery like a PC or a server. It can, for example, interact with humans, it can interact with its environment, and I think that all those things are things that can lead us to enrich the learning process and maybe open up possibilities that didn't exist before. So, of course, this isn't a super new idea. Already in 1991, Rodney Brooks, one of the pioneers in the field of robotics, has said that mobility, acute vision, and the ability to carry out survival-related tasks in a dynamic environment will be the basis of true intelligence. So I took this to heart and came up with the following idea. Rather than having a static process that is always the same, I instead propose to close the loop in a way. So we would start out with the same starting point, right? We would have static data sets that we use to pre-train a model, that we deploy it, then run inference on it. But however, now we close the loop by continuously collecting data and retraining the model. And the way I propose to do this is with without human interaction. So no labeling, no active, no active tasks that have to be done by a human, and to do it in a continuous time as possible. So not every 2 weeks, not every month, but rather after every deployment or even during deployments to retrain the model so that it's always fitting to the current situation the robot operates in. So I propose to do this using the intersection of 3 areas of machine learning that I think are very interesting to solve this kind of tasks. And these are, first of all, and primarily unsupervised learning, reinforcement learning, and active learning. And today I just want to talk a little bit about each of these aspects in my current research. To this end, I would just like to start out with unsupervised learning. So just for the people who maybe did not hear about this, unsupervised learning is a way to generate meaningful representations or features from machine learning models without having dedicated labels. So in order to achieve this, right, because labels are very expensive to generate, we need a bunch of students, probably many people in this room have done this already and kind of cursed their lives for a couple of hours every day just drawing boxes or labeling classification data. It's a very tiresome process. So instead, what unsupervised learning presents is the possibility to kind of extract the image, the label from the data itself. So this can be done, for example, with augmentations. And here I have some representative examples from the beginning of this field, where people would basically try to predict, or they would rotate an image and then ask the neural network to predict the rotation it is in. Or another historical example of this would be this colorization task, where we would take the black and white, make an image black and white, and then ask the neural network to reintroduce the color. Why is this meaningful? Because that way we, in order to generalize to a huge amount of data, to a very diverse data set, in order to colorize the image back, the network has to learn what the things in the image are. Right? So it has to learn to differentiate, for example, the fish from the stone. And we can use those features then in downstream tasks, like, for example, classification or object detection. So this was the history, like maybe let's get a little bit to the state of the art. And these pretext tasks have changed a little bit. So we still use the core idea of augmenting an image and then predicting something from it. But these newer methods, for example here, Dino, a state-of-the-art method from Meta Research, they use this a little bit differently. So here, for example, we have an image of code, and now we have basically 2 copies of the same network, a student and a teacher. And we present both of them with like little snippets of the image. You can see those are different snippets. So here, this one is the upper one is a more zoomed in one, but the other presents a more zoomed out view, as well as they have some augmentations done to them. Right? So this is the contrast and whatnot is changed between the 2 samples. And now the task of this network is to predict a representation, a vector for both of them that is the same for both of these similar views of the image. Why is that suitable? Because obviously they show the same object just from a kind of different perspective, and therefore we want to encourage that the representation of this is the same. And for reasons that sometimes seem a little bit magic to me, this works in generating very, very good representations for in feature space. So here are some examples where we do this on not just one, but many, many millions of images. We kind of have these kinds of visualizations. So this is just the raw features of the network visualized, and we can see that it clearly can discern objects from each other. And you can use this also very successfully for classification or object detection. You also have a little video. I hope you can my basis. The idea is to bring this a little bit to the robotics world and to bringing the idea of this physical presence. So I propose that we kind of do this mechanism of taking an image and looking from it from different perspectives that we also saw here. We do this quite naturally. For example, when we walk around an object, right? So we also have this mechanism where we, like here, can take different views of an object while navigating 3D space, and we are always aware that this is the same object. This is called object permanence psychology. So this is my idea, basically, to bring this to the robotics world, to generate these augmentations naturally from a robot basically moving in space, and using these different perspectives as the input to this network. So first of all, I did this with on synthetic data to kind of make a proof of concept, and very helpful for this was the data set called Observers. Observers is a very big data set of roughly 800,000 object meshes. So these are not just images, but rather full 3D models, and we can render them using Blender, for example, from any perspective that we want. So these are just some examples here. We have bananas, we have bikes, so a very diverse data set. However, it was quite a challenge because rendering those objects is not that easy. So doing it naively, just taking Blender and running it would take several months to generate the whole data set. So instead we had to make like a headless distributed system running many of those processes at once to generate the data set. But once we were done, we were left with roughly 4 million images. We didn't process all of those images, all of the objects, but rather roughly half, and we came up with those 4 million images from different perspectives. So yeah, we did this. We then input these images into these dyno networks, and we also took baseline readings from the normal method without introducing the different perspectives. So what wasn't so nice about this whole thing, we don't have many or a lot of data to actually verify if it's working in terms of classification, because the subset of the data of the objects that are labeled correctly in this data set is very small, because they scrape them from the internet and they come with kind of obscure file names and whatnot. So we in the end had only around 10,000 samples that were correctly labeled, which isn't that much, unfortunately. So yeah, but we did some experiments on this nonetheless, and we can see those are accuracy plots from a still a little bit under-trained evaluation, but we can still see that this green line, which is our proposed version that takes into account this 3D perspective, is constantly outperforming the standard dyno, which is here orange, in a quite substantial way. So we could achieve 3-4 percentage points of increased accuracy, which was quite nice. So this is done with the linear classifier on top of a frozen feature extractor to go into details. So yeah, this was maybe the first pillar of my current work. Now let's get a little bit to the active learning part. If you remember the Venn diagram, and this is the active learning. And what I built here is a pipeline for data augmentation. In my use case, it was VQA, so visual question answering, the task where you basically take an image, input it into a network, and ask the question also with the image. For example, what animal can you see in the image, or what are the women holding, or whatever else questions you can think of, and then asking the model to come up with answers. This is a quite hard task because it requires a lot of effort also to annotate, because you actually have to sit down and write out questions and find the answers and whatnot. So coming up with a data set for this task is not easy. So what we propose is to generate synthetic labels for them by leveraging the current state-of-the-art image generation models. So if you heard about Stable Diffusion or Flux or DALL-E or whatever, this we use here to introduce alternative answers into the original images. For example, here you can see A, C, E, and G are the images contained in a baseline data set. And for example, here the question would be, which animal can you see in the picture? And the answer from the original is, of course, sheep. And while we change the answer in the image, so it says cow, right? Like this, we can achieve an additional image question pair from the original data. How we do this, or what's the pipeline? So this is the original image. It comes with a question, right? So what is the woman buying? Here the original answer is bananas, right? And then we try to come up with alternative answers. Of course, we need to do this in an automated way. So we input the question and answer into a language model like ChatGPT, for example, and ask it automatically to come up with sensible alternative answers. So here, a set of alternative answers could, for example, be apples, right? And whatever else you can think of. Then the next point, the next part is using an open vocabulary detection model to find the original answer in the image. So because we don't want to change the entire image, because of course those generators aren't perfect. So we want to just change the smallest amount of area in the image as possible. So we try to find the original answer in the image. Here we have identified it with the bounding box, and only in this area we perform the actual substitution to induce the answer, and then thus we have another pair of images to train on. You can imagine doing this for not just for this task, but also for object detection tasks, for example. And then we can use this to actually train a model. We did this, train this VQA model, which is basically an LLM model with some additional bells and whistles. So we took a lava or tiny lava and fine-tuned it on our additional data set, and we could achieve a percentage increase. This is the lower left corner, the overall metric of roughly 0.3 percentage points increases, which doesn't sound like a lot, but in the public rankings where people have like leaderboards of these models, this is roughly a difference of 3 or 4 places in this leaderboard. So this is very tight margins, and we could achieve rather nice results with that synthetic data. So yeah, and coming maybe to the final aspect of this research direction is the reinforcement learning. And here we wanted to use reinforcement learning to train an agent existing in a simulated world to capture additional data for training. So just maybe a short demo of a video how that looks like. I hope you can see it. But this is a model trained with a reinforcement learning algorithm to drive around in a city environment, and we added some additional parts to this, which I will introduce in a second. So of course it operates just fine in the city. It kind of drives around, but it also does more. And this can be a little bit summarized here. So we added a so-called curiosity signal, or also called an intrinsic reward. That means this is, if you're familiar with reinforcement learning, usually the loop is that your agent does something in an environment, and by sampling the state transition to the next state, you also receive a reward from the environment, so to speak. So how well are you doing on the current task? This introduces the intrinsic reward, so a reward that comes from within the agent. And here this reward models curiosity by trying to predict here. So this one tries to predict the next state and then compares it to the actual next state. So this is this box in the lower right. And based on the difference of my prediction of the next state and the actual next state, I kind of can, by proxy, judge if my expectation matches reality or the agent's expectation. Curiosity reward, while the right side has this reward present, and you can see that while the left side didn't go to some areas at all, the right side explored all of it. And in fact, I think the most curious part is in the lower left, where it actually went into the park. It was so curious to go into the park that it even went off the road, which was primary report to stay on the road. So it was so curious that it just wanted to explore here as well. Yeah, and couple this with some mechanisms to see if there are objects in the foreground. So here, for example, we have on the left the image from the simulation. Then we take a depth image from the simulation, and if we detect an object, something that is in the foreground, we take an image of it. We capture it, we store it to our data set, and then you can imagine could bring it back to the first method that I showed you, and so to speak, close the loop. Yeah, so those are some more examples of this captured data from the simulation, hoping to bring it at some point to the real world as well. But yeah, in the meantime, that was all. Thank you very much, and I welcome all of your questions.
Okay, Jakub, can you hear me?
Yeah.
Perfect. Thank you, Jakub, for your insight. Can you hear me, please?
Yes, I did hear this.
Thank you. And my question are related to that reinforcement learning, and first for self-supervised vision transformer. For self-supervised vision transformer, is it necessary to have rendering and augmentation to, train those and to have that sort of classification when we are getting around 1/4 of total accuracy as compared to the other models? Why that lowest accuracy is preferable in your case? And my second question would be related to that reinforcement learning. Is it possible that our model can go off policy and off model to see, particularly in agriculture sector, where we do not have defined reward function or defined policy for any learning models? Can it be possible to deploy that model in our agriculture application? Can you say, please?
Yeah, so let me start with your second question, because the first one you have to rephrase, because I didn't get it quite. But yes, of course, we can use the reinforcement models in agriculture as well. For that, well, you have to maybe see what the cost benefit is, because if you have a structured environment, if you have a field with rows or whatever, then it's probably not that beneficial to use a reinforcement learning algorithm, because the sampling efficiency is not that high. You would need a lot of data, you would need a lot of training time, and also it's difficult to do this in the real world because just resetting your robot is basically kind of hard once it fails. So this is why the simulation is very nice because you can just reset it to an initial point at any time the robot would do something wrong, whereas in the real world this could have like potentially catastrophic consequences for the robot. So if your agricultural environment is structured, then I think classical algorithms would be nicer for that. But if you do deal with an unstructured environment, then definitely reinforcement learning can also be a possibility. And then for your first question, unfortunately, I didn't quite hear it completely, so maybe you can repeat it.
Rephrase it for you. In shorter term, I want to ask that for Vian transformer, is it necessary that we should have rendering and augmentation? And linked to that, why would we do such a laborious task when we are getting only 25% accuracy?
Yeah, so this is the reason for that is that basically here we wanted to show a proof of concept and that we achieve higher results than Dino, which we did on a very, very low training budget. So whereas those models are usually trained for 300, 400, 500 epochs, we did it for 20 to 30, and this already took us a couple of days. So this was more of a proof of concept. Now we have to scale it up to bring it to the full accuracy, but these models, if you take them as they come from meta research that are trained on the hundreds of millions of images, they have image net accuracies of about 80%. So these are state-of-the-art models. So this is just due to some training constraints that we have, that this is a lower number.
Does anyone else have any questions?
Yeah, I can ask.
Okay. Jakub, there is one more question.
Yeah.
Thank you very much for a very interesting presentation. I'm actually from the NLP world, so I was just thinking about it. Like you have mentioned VQA. Can we extend this methodology for RAG for images which are in our private repository? So for example, there are images in private repository and I need to apply VQA. Can we extend this approach somehow that can answer our problem?
Can you repeat what domain you want to extend it to? I didn't quite catch that.
Yeah, so we have the VQA task, and I have certain images which are there in my private repository, so they are not available to the LLM. And I want to ask certain questions related to those images. Like this is an image that I have put input to the network, and I want to ask how many people are there, for example. But that image is not available to the LLM when that LLM was being trained. So I was just thinking about it. Is there any way to extend this approach where we can answer VQA type questions for data which is available in our local repository?
Sorry, the audio quality is not reaching it well, but I think the question was if we can extend it to other domains, and basically yes. So I think the prerequisites are that it's an object-centric question that can be answered from within the image. So there's also VQA, kinds of VQA where, for example, there you would have a can of Coca-Cola, and then you would ask the model who is the producer of this can, or where was this can produced, or something like that. So things that are not directly answerable from the image itself are kind of hard to do in this fashion. I think once you can boil down your data sets to objects that are replaceable in a donor image or source image, then it's extendable, of course. If you have to change the entire image, then it becomes difficult because you can't rely too much on these
Thank you, Mr. Pawlak, for that fascinating look into the world of robotics and machine learning in agriculture. That concludes our presentations for today. I would like to extend our heartfelt thanks to all our distinguished guests for delivering such comprehensive and insightful sessions. Their research and expertise have greatly enhanced our understanding of how remote sensing technologies are shaping the future of precision agriculture and contributing to more sustainable farming practices. I would like to highlight some key takeaways from today's workshop. We have gained valuable insights into how cutting-edge technologies like multispectral and thermal imaging combined with UAVs and IoT can be used to monitor crop health, optimize resource utilization, and manage environmental challenges. This workshop has also underscored the importance of integrating these technologies to improve decision making in agriculture. We hope that today's sessions inspire new collaboration and innovation in the field. Thank you all once again for your participation in this event. We look forward to continuing these important conversations and fostering further advancement in precision agriculture. Assalamu alaikum and have a very wonderful day. Please proceed to Jinnah Mess Hall for lunch. We will have an afternoon session as well after lunch. Thank you.
Jakub, that concludes our morning session. Thank you so much.
आपने कैसे किया 3 प्रकार के नष्ट